So hopefully, third time's the charm. I've actually got it recording my voice now. Maybe. Seems to. Cool. All right. For my problem, I chose problem 5.7, which is out of chapter 5, the beginning of which is lumped capacitance. So that's what we'll be doing in this problem here. To go ahead and read it off in the problem's pretty broken English. Some steel balls of 10 millimeter in diameter are annealed by heating them to 1150 Kelvin, and then they are slowly cooled to 450 Kelvin in an air environment in which the ambient temperature is 325 Kelvin. There is a convective coefficient of 25 watts per meter squared Kelvin. The steel properties are K equal to 40 watts per meter Kelvin. The density is 7,800 kilograms per meter cubed, and with a specific heat of 600 joules per kilogram Kelvin. And what we're supposed to do here is estimate the time it takes from it to go to, or sorry, for it to go from 1150 to 450. So, all right, using my little pointer here, I drew that. Pretty simple. Just you have your steel ball there. It's very hot. It's going convecting out to T ambient. It is 10 millimeters in diameter. Not much there. We have our givens and our assumptions. For assumptions, I said steady state, constant properties, because the steel is not exactly changing, uniform convection, and I said neglecting conduction and radiation, because it said nothing about small object, large environment, nor did it sit, or while even though I drew it sitting on something, because it felt wrong to have it just sitting out there in space, there's no conduction going to that. So we're going to ignore that. All right, to start off, we have our analysis. For any problem relating to lumped capacitance or any of the other ones, what's it? The two other ones. Hold on, now I'm going to blank. Semi-infinite and first term, we have to start with the Biot number. So the equation for that is the convective coefficient times the characteristic length over K. And for a sphere, like the one we have here, the characteristic length is radius over 3. So going ahead and plugging all that in, we get 0.001 for that. And for us to be able to use the lumped capacitance method, it has to be less than 0.01, and we're about 2 orders of magnitude less than that, so we're good to go. All right, so for the next part, we have a convective transfer, or sorry, a convection heat equation here. So we have the temperature, which we want at time unknown t, minus T ambient, equal to the starting temperature T1 minus T ambient times the exponential here of time over time constant. Now we know all these except for time constant. So we're going to go over here and calculate that. The equation for time constant is density of the steel times the volume of the steel times the specific heat of the steel over the convective coefficient times the area. This is, I believe, surface area. So we're going to go ahead and cancel about a bunch of those numbers that we don't need to otherwise calculate, and it leaves us with this. And that gets us 312 when we plug it into the calculator. Doing a quick unit check here, we cross out everything, and it gets us joules per watt, and watts are just joules per second. So that simplifies to seconds, which makes sense because if we go over here and look at this unit check, we've got Kelvin minus Kelvin, Kelvin, same thing over here, but we have the exponential, and we want those seconds to cancel with those seconds, so everything works out. So that makes sense. Cool. So plugging in our 400, 325, 1150, and 325, and our 312, we can go ahead and just math it out, simplify going down, use the natural log to cancel that e, and we get our time equal to 588 seconds, or about 9.8 minutes. And with that, we're done.